NASA should never strike an interstellar object, 3I-ATLAS. While the world scrolled, slept and stirred their morning coffee, something quiet detonated inside NASA. No broadcast, no breaking news, just a single PDF uploaded in the dark hours to the Minor Planet Center, Bulletin 2025 U-142. 16 lines of emotionless data, no adjectives, no alarm. But hidden between the coordinates and reference codes was a signal that should never have been triggered. The International Asteroid Warning Network, humanity's shield against extinction-level impacts, had been switched on, not for an asteroid, not for anything we've ever charted, but for a traveller from beyond our solar system, 3I-ATLAS, a comet that doesn't behave like one, an object that wasn't supposed to exist here. Now the world's most advanced defence systems are quietly tracking it. No press release, no comment, just silence and eyes in every orbit. So the question becomes, what did they see? And why now? This is the 3I-ATLAS channel, calm, focused and based on real-time solar system data. If you want to be part of this mission, hit subscribe right now. Comment ATLAS below to enter the giveaway for our exclusive 3I-ATLAS hoodie. Tell me where you're watching from and the exact time it is. You're now part of a global community tracking something the textbooks never prepared us for. On October 27, 2025, an internal signal was triggered inside NASA's Planetary Defense Coordination Office. It wasn't a warning to the public. There were no press conferences, no bold headlines, and no dramatic statements on mainstream media. But in the background, something quietly escalated. A planetary defense protocol typically reserved for civilization-ending asteroid threats was initiated, and the target wasn't a known asteroid. It was 3I-ATLAS, and officially it wasn't even a threat. To understand the magnitude of what happened that day, you have to understand what this protocol is, and what it isn't. NASA's Tier 4 planetary defense protocols are not activated for routine observations. These protocols form part of the continuity infrastructure, a system built in coordination with the Department of Defense, the Federal Emergency Management Agency, FEMA, and international space agencies like ESA and JAXA. These measures are rarely discussed publicly because they are designed for catastrophic events. In the internal hierarchy, Tier 4 refers to active monitoring of an object deemed non-predictive, potentially accelerating, and non-conforming to standard gravitational modelling, even if the object is not currently on a collision course. Tier 4 does not require that an object be heading toward Earth. It requires that the object behaves in a way we don't understand. 3I-ATLAS fits that profile precisely. This protocol was originally designed for extreme edge cases, rogue asteroids exhibiting Yarkovsky drift, fast-spinning tumblers that might shed mass en route, or fractured bodies with unstable debris clouds. But this time, the activation didn't come from a known hazard. It came from a series of anomalies stacked too tightly to ignore. First, the object's brightness curve, its light signature over time, failed to match its predicted mass or tail composition. Then, telemetry from ESA's ground network showed orbital deviation, not in direction, but in velocity symmetry. That is, the object's forward momentum was correct, but its angle of solar deflection was off by a margin consistent with either propulsion or thrust-like outgassing, yet without any matching emission event. At that point, internal sensors flagged the object as intermittent class. In NASA's own terminology, an intermittent class object is one whose telemetry becomes periodically unmodelable, where expected data diverges from reality at predictable intervals. Historically, these flags were generated only twice before, once during the 2004 Apophis trajectory recalculations, and once during the fragmentation of Comet Elenin in 2011. But in both cases, those anomalies had clear explanations: gravitational perturbation, solar heating, debris field evolution. 3I-ATLAS offered no such clarity, so why activate a defense protocol for an object 270 million kilometers away from Earth? Because its behavior was pre-perihelion, not post. In other words, the object was already behaving unpredictably before reaching the most dangerous phase of its solar passage. Perihelion, the point at which a comet is closest to the Sun, experiences the highest gravitational stress and, crucially, becomes invisible to Earth due to solar glare. If a maneuver were to occur, a shift, a fragmentation, a course correction, perihelion would be the moment to do it. and for the first time in planetary defence history, the object in question wasn't gravitationally bound to our solar system. 3I-ATLAS came from interstellar space. That alone made it unique. But the irregular trajectory, the gamma emissions, the unexplained compositional data, those pushed it into a different category, something that could not be explained. And NASA's systems are not designed to wait for public consensus. They're designed to act first. That's why the protocol was activated. Not because 3I-ATLAS is heading toward us, but because if it ever decided to, we'd have almost no time to respond. And right now, no one can say for certain what it will do next. When you study orbital mechanics, there's one golden rule: gravity doesn't improvise. Every object that moves under its influence follows predictable laws. Whether it's an asteroid, a comet, or a probe, once its position, velocity, and mass are known, its path can be modelled years, sometimes decades, into the future. Tiny deviations can occur, of course, but they are explainable. Solar radiation pressure, outgassing, gravitational tugs from planets, every one of them leaves a mathematical fingerprint. But the trajectory of 3I-ATLAS doesn't fit any of those fingerprints. On October 25, 2025, 2 days before NASA quietly triggered its planetary defence protocol, the European Space Agency's Deep Space Tracking Network logged something subtle but significant. The object's predicted orbital path diverged by 0.08 arc-seconds. On paper, that seems microscopic, barely measurable. Yet, at its speed of 68 km per second, that deviation translates to a positional drift of over 50,000 km near perihelion. In cosmic terms, that is enormous. And worse, it wasn't random. It was consistent. The anomaly repeated every 36 hours. The object appeared to be making tiny corrections, like something subtly altering its course, not chaotic outgassing, but calculated adjustments. At first, ground-based astronomers assumed it was a data artifact. Calibration errors, perhaps. After all, 3I-ATLAS was approaching the Sun, and solar interference can distort light measurements. But when multiple observatories on separate continents, Chile, South Africa, Japan, reported the same angular drift, the statistical probability of coincidence collapsed. Something was moving the object. To understand why this was so disturbing, consider how normal comets behave. As they near the Sun, heat causes ice to sublimate, producing jets of gas that can slightly shift their paths. This is called non-gravitational acceleration, and it's well documented. But those shifts are irregular. They follow thermal cycles, they spike with rotation, and they leave optical traces: jets, flare-ups, tail distortions. 3I-ATLAS displayed none of that. No thermal surges, no visible plumes. Its tail remained geometrically perfect, yet its trajectory kept bending by tiny, repeating increments. The pattern was not chaotic, it was rhythmic. Astronomers began comparing this rhythm to internal spin models. If 3I-ATLAS were tumbling, the drift might correspond to rotational exposure, outgassing from alternating sides. But radar reflection data from the Goldstone facility showed no measurable spin rate. The object wasn't rotating in any way that could explain the motion. That left only three possibilities: an internal pressure differential, some kind of venting mechanism synchronized over time, a structural collapse, mass redistribution inside the nucleus, a controlled burn, intentional thrust. NASA's internal modelling quickly ruled out the first two. The energy required to maintain such a stable rhythmic pattern over days was too precise, the direction of the drift too linear, and the magnitude exactly within the threshold of a controlled deceleration. By late October, orbital analysts at JPL privately coined a new term for it: trajectory dampening event. This wasn't acceleration, it was the opposite. 3I-ATLAS was slowing down. Not dramatically, just enough to suggest something was resisting its natural momentum. If the object had been purely gravitational, it should have gained speed as it dove toward the Sun. Instead, its relative velocity decreased by almost 2 kilometers per second between October 23rd and 26th. The implication was staggering. Either the comet was releasing mass in a way we've never seen before, or something aboard it was actively reducing velocity. A braking maneuver. That single metric, an interstellar object slowing down, was enough to trigger quiet panic inside NASA's Planetary Defense Coordination Office. Because no known natural process can explain deliberate deceleration in deep space. Only engineering can. And as the data poured in, one chilling realization became harder to ignore. 3I-ATLAS wasn't just drifting through our solar system, it was navigating it. On October 3, 2025, 3I-ATLAS performed a near-flawless flyby of Mars, passing within 30 million kilometres of the red planet, close by cosmic standards, especially for an interstellar object. From a scientific standpoint, this was a gift. Mars isn't just a dusty neighbour, it's one of the most heavily monitored planets in the solar system. Orbiters, rovers, landers, all equipped with high-resolution instruments. A total of 6 active spacecraft, including NASA's Mars Reconnaissance Orbiter, MRO, and ESA's Trace Gas Orbiter, TGO, were in position. With advance notice, the fleet had every opportunity to capture world-class observations of 3I-ATLAS. And yet, something strange happened. ESA released only 5 frames, low-resolution, grainy composites. The images showed the object as a soft white blur against a background of starfield noise. No spectral overlays, no trajectory tags, no thermal analysis. From NASA, nothing. Not a single high-resolution image, not a single data point, not even a press release. And this silence wasn't just surprising, it was inconsistent with protocol. Historically, when a major comet or asteroid passes close to Mars, NASA responds with enthusiasm. In 2014, for example, Comet Siding Spring made a similar pass, and MRO captured multiple high-resolution shots, which were shared publicly within 72 hours. Press conferences were held. Spectral data was uploaded to NASA's Planetary Data System for open access. But with 3I-ATLAS, the most anticipated interstellar visitor in years, the silence was total. Internally, members of the planetary science community began asking questions. A few researchers reported that observation windows had been booked months in advance for MRO's high-rise camera, capable of resolving surface features just 30 centimetres across. In theory, it could have resolved 3I-ATLAS's coma, tail structure, or even activity near its nucleus, offering insight into shape, spin, and surface texture. Instead, radio silence. When pressed, a NASA spokesperson issued a boilerplate statement. Due to limited spacecraft resources and prioritization of surface operations, Mars orbiters were not able to capture significant data of 3I-ATLAS during its October 3rd flyby. But that didn't match internal logs. Multiple observation sequences had been preloaded into MRO's command schedule weeks earlier. So what happened to the data? According to internal emails leaked by a contract technician at JPL, the images were taken, and the data was downlinked. But as of October 27th, the image packets were flagged for restricted review, a rarely used classification typically reserved for national security-related satellite observations. This raises an even more important question. Why? If the object was behaving normally, if it simply appeared as a dusty interstellar snowball, there would be no reason to hide the footage. NASA has never classified comet images before. Not from Mars, not from deep space, not even when objects posed theoretical risks. But something about 3I-ATLAS's approach seemed different. ESA's 5 blurry frames suggest the object maintained a stable trajectory, but lacked the typical coma distortion seen during high-speed flybys. No tail curvature, no brightening, just a clean, precise arc through the Martian sky. Moreover, the absence of spectral data is telling. Instruments like TGO's Cassis or Mars Express's Omega are designed to capture reflected sunlight at high fidelity, especially in the infrared and ultraviolet ranges, which are key for detecting water vapour, organic molecules, and metallic ions. Nothing was shared. One theory quietly circulating among scientists is that the Mars flyby revealed surface detail inconsistent with a natural body, perhaps polygonal symmetry, perhaps heat distribution that defied thermal modelling, or most ominously a lack of expected volatile emissions at close range. If the object wasn't outgassing near Mars, then its previous light curve may have been manufactured, simulated, misdirection. Because if 3I-ATLAS passed Mars without shedding material, while still showing a bright coma from Earth's perspective, then someone or something was controlling the way it appeared from different angles. In short, the Mars flyby wasn't just a missed opportunity, it was the moment when NASA stopped sharing. And the gaps in that silence may say more than any image ever could. The Solar and Heliospheric Observatory, better known as SOHO, has been one of humanity's most valuable tools for watching the space around our Sun. Its LASCO instrument, short for Large Angle and Spectrometric Coronagraph, is designed to do one thing exceptionally well: block out the blinding light of the Sun so that we can observe the environment around it. From this unique vantage point, LASCO has given us some of the most iconic images of solar flares, coronal mass ejections, and yes, comets diving into the Sun's corona. Hundreds of solar-grazing comets have been recorded this way, many of them disintegrating dramatically in full view. But during the critical window, between October 23rd and 26th, something went missing. That window, which coincided with 3I-ATLAS's final approach to perihelion, should have offered a perfect opportunity. The object was crossing into SOHO's field of view, close enough to register, but not so close as to be fully eclipsed by the Sun's disk. Scientists had been waiting weeks for this. LASCO was expected to capture the object's acceleration phase, plasma interactions, and possibly even structural changes as it entered peak thermal stress. Instead, the data feed from LASCO showed a gap, a precise, quiet void. The missing frames weren't corrupted, they weren't noisy, they were just absent. At first, most assumed a technical glitch. LASCO has experienced occasional downlinks issues over its 28 years of service, but this time was different. The blackout wasn't random, it was selective. From October 23rd at 03:12 UTC through October 26 at 11:46 UTC, LASCO's wide-angle C3 coronagraph showed no recorded entries in the comet's expected path corridor. This 3-day silence perfectly overlapped with the time frame in which 3I-ATLAS was predicted to enter its highest velocity curve, nearing perihelion, its closest, fastest point in orbit around the Sun. And this wasn't just any period of observation. This was the final observable window before the comet disappeared fully behind the Sun. Once it crossed that solar conjunction line, it would be invisible to Earth-based telescopes for weeks. The public archive for LASCO images shows nothing unusual, at first glance. But digging deeper, astronomers noticed that neighbouring timeframes were recorded normally. Frames at 03:11 and 11:47 appear fine. Only the narrow slice aligned with 3I-ATLAS's vector path is missing. This kind of surgical absence doesn't happen accidentally. It happens when someone, or some system, decides to redact. To make matters more suspicious, the SOHO mission's automated tweet feed, which routinely posts LASCO imagery and solar flare detection updates, also went silent on October 24th. No scheduled tweets, no system alerts, no references to 3I-ATLAS. Then, on October 27th, just after the gap ended, NASA's Planetary Defense Coordination Office quietly activated a monitoring protocol. The timing wasn't just close, it was immediate. That's when researchers began to connect the dots. If 3I-ATLAS made any trajectory change, mass ejection or rotation correction, it would have happened during that gap. The last moment we had a line of sight from SOHO before the comet vanished behind the Sun's glare, and yet no public statement was made, no apology, no explanation. Why does that matter? Because SOHO is not classified, it's a public observatory, funded jointly by NASA and ESA. Its data feeds are open, its archives are accessible in real time, which leads to one unsettling question. If the data wasn't corrupted, then who deleted it, and why? Some believe the missing frames showed something that couldn't be explained, perhaps a flash, a course deviation, or a separation event. Others think the gap was a preemptive move, a calculated decision to ensure that whatever happened during perihelion remained unobserved. But in a universe governed by light, missing frames are not just a technicality, they are silence, and silence at the edge of the Sun is never accidental. October the 29th, 2025. The interstellar object known as 3I-ATLAS reached perihelion, its closest point to the Sun. At that moment it was moving at a staggering 68 kilometers per second, faster than any spacecraft humanity has ever built. It was also completely invisible to Earth-based telescopes hidden in the solar glare. This was not just an astronomical milestone, it was a strategic window. Because in the world of orbital mechanics, perihelion isn't just a point of proximity, it's an opportunity. And if there were ever a moment for something extraordinary to happen, this was it. Let's explain why. The physics of perihelion. In spaceflight, there is a well-known principle called the Oberth effect. It's not speculative, it's math. When an object is at the lowest point in its orbit, the point where it's moving fastest relative to the body it's orbiting, any propulsive force applied there has maximum impact. A small burn at perihelion can shift the object's path drastically, allowing it to shed speed, change direction, or even enter a new orbit altogether. If 3I-ATLAS were a spacecraft, this would be the ideal place to perform a major manoeuvre. You do it here to conserve energy, optimise trajectory, and, most importantly, to do it when no one could see you. And 3I-ATLAS had 8 uninterrupted days of solar cover, from October 21 to October 29th, in which any trajectory change could occur, completely shielded from Earth-based instruments. What would a manoeuvre look like? A natural comet would experience thermal stress at perihelion. Ice sublimates. Gas jets erupt. The tail flares out. Maybe some fragmentation occurs. These are chaotic, observable effects. But with 3I-ATLAS the story is different. As it approached the Sun, the object's light curve remained suspiciously stable. No dramatic brightening. No sudden flares. It was too clean, like a controlled descent. Now imagine, hypothetically, that the object wasn't entirely natural, that it had internal systems, a means of propulsion, even a limited capacity to steer. Perihelion would offer an irresistible set of advantages: maximum energy efficiency for any manoeuvre, minimum visibility thanks to solar glare, gravitational masking allowing small adjustments to look like orbital drift. In military terms, this is a stealth corridor, a blind spot in the surveillance grid. The timing is too perfect. Let's go back to the calendar. October 20th sees 3I-ATLAS enters conjunction. October 25th. It is struck by a direct CME, coronal mass ejection, from the far side of the Sun, a billion-ton blast of plasma. October 29th. The object reaches perihelion. October 30th. Theoretical consciousness event claims gain virality. October 30th. The object begins emerging from the Sun's glare. Now consider this. If 3I-ATLAS executed a course change on October 29th, during maximum shielding and thermal energy input, we would not see the effects until mid-November. The orbit would continue to appear nominal for a while. But slowly, the deviation would build, a slippage in predicted velocity, a slight drift in its apparent path, a brightness offset. And according to analysts, that's exactly what happened. Starting in late October, tracking centres began noting unexplained drift, subtle changes in velocity vector and even offset light emissions, not from the centre of mass, but from an area beside it. A signature not of chaos, but of manoeuvring. A window, meant for silence. NASA never officially declared anything abnormal at perihelion, neither did ESA, but they did activate Tier 4 planetary defence protocols within 48 hours of the event, and they began retasking every major observatory to track the aftermath. If the comet performed a burn, natural or artificial, this was when it happened, in the narrowest blind spot in the solar system, at the fastest point in its journey, behind the most powerful light source in the sky. Perihelion wasn't just an orbital checkpoint, it may have been a moment of transformation, and we won't know what truly happened there. Until 3I-ATLAS finishes emerging from the Sun's shadow, on October 22, 2025, 3 days before the LASCO blackout and a week before perihelion, an alert was triggered aboard NASA's Fermi Gamma Ray Space Telescope. The system had detected a steady emission of high-energy photons coming from a position that matched 3I-ATLAS within a margin of 0.03 degrees. At first, the signal looked like background noise, a faint band of energy around 2.4 mega-electron volts, stable, consistent, and oddly narrow. But within hours, it became clear that this was not noise. It was persistent, and it was focused. Gamma rays are not subtle. They are the most energetic form of light known to physics, released in the most extreme environments the universe can produce, the magnetic poles of neutron stars, the death throes of supernovae, or the event horizons of black holes. They do not come from frozen comets or inert chunks of rock. For a body like 3I-ATLAS, which should be little more than ice and dust, to emit a continuous gamma-ray signal was not just unusual, it was impossible. The Fermi team watched as the signal held steady for nearly 18 consecutive hours. There was no pulse, no decay curve, no random scatter. just a clean, unwavering emission line, as though a switch had been flipped and left on. Natural processes do not behave this way. Even gamma rays from solar flares fluctuate chaotically. The emission from 3I-ATLAS remained locked at the same amplitude, oscillating only slightly every few seconds, as if something inside the object was cycling through a regular power phase. When cross-checked with other instruments, ESA's Integral Observatory and Japan's Maxi telescope aboard the International Space Station both recorded the same energy signature. That triangulation eliminated the chance of a false reading. It meant that 3 separate instruments, operating in different orbits and using different sensors, all saw the same thing in the same place at the same time. Within minutes, the Fermi data stream was encrypted and removed from public access. The event ID was replaced with a placeholder, calibration anomaly. Internally, however, the anomaly was treated very differently. Preliminary analyses described the signal as steady, coherent, and non-thermal. In astrophysics, non-thermal means it was not generated by heat or radiation from chemical reactions, the usual source of comet emissions. It meant the photons were being produced by an unknown energy process. The working term that circulated among analysts was artificial modulation. No one said propulsion out loud, but the implication hung in every email. Roughly 12 hours after the alert, a thread appeared on social media from an account that had previously posted updates about European satellite operations. The author claimed to work as a debris analyst at ESA and stated that Fermi has locked a stable gamma signature on Atlas. Constant output, not random. They're calling it an engine tone. The post was deleted within an hour, but screenshots spread rapidly. ESA never acknowledged or denied the claim. NASA simply declined to comment. The signal itself ended abruptly, not fading but cutting off entirely, as if a transmission had been terminated. No afterglow, no decay, just silence. That instant cut-off was perhaps the strangest feature of all. A natural burst loses energy gradually. Only a controlled system shuts down in a single frame. When the data archive reopened 2 days later, the event file had been replaced with a generic system log. To this day, no agency has released the raw photon counts or the full temporal profile, but what little leaked through suggests a pattern, a rhythm too precise to be cosmic chance. For the first time, an interstellar object had not just reflected the sun's light or emitted dust and vapour, it had radiated structured energy. In plain terms, something inside 3I-ATLAS was active. On the night of October 22, 2025, while astrophysicists quietly processed the unexpected gamma-ray emission linked to 3I-ATLAS, a new ripple began to spread, not through scientific channels, but through the chaos of social media. At 19:03 UTC, an anonymous user posted a multi-part thread on Platform X, the site formerly known as Twitter. The account had existed for nearly 5 years, mostly dormant, except for the occasional repost. From European launch facilities and satellite deployment bulletins, it had less than 400 followers and followed no one. But the language of the thread was not casual. It was surgical, laced with technical accuracy, timestamps, internal references, and very specific claims. The user claimed to be a space debris engineer and orbital analyst contracted by the European Space Agency, ESA, stationed at a facility responsible for processing raw telemetry from Integral, ESA's gamma-ray observatory. The thread, now widely known as the Atlas leak, began with a chilling line. The public is being misled. The Fermi signal from 3I-ATLAS is real. It was stable, it was flagged, and it was classified within 2 hours. From there, the thread detailed a first-hand account of how the detection was received internally. According to the whistleblower, the gamma-ray burst seen by Fermi was cross-referenced almost immediately by the Integral team in Darmstadt, Germany. Within 45 minutes of correlation, access to the raw observation files was locked. Staff were told it was a calibration cross-check and not to discuss the signal externally. The whistleblower disagreed. They claimed the signal was already flagged internally as non-stochastic, meaning it did not behave like a naturally occurring random event. Instead, it showed coherence, modulation, and directionality. In technical terms, it had the hallmarks of an engine signature. Not propulsion in the classical sense, but an energy source. One that was holding steady against solar interference, maintaining spectral integrity even as the object approached perihelion. It's not leaking, it's broadcasting, the post read. It's a constant power signature, and someone decided the public doesn't need to know. In one of the most damning claims, the whistleblower said the signal was never circulated through ESA's science division, which would normally analyse anomalous data for peer review. Instead, it was routed through an administrative pipeline labelled DFRSREUX, a rarely used designation for events deemed sensitive to EU defence agencies. That meant the data wasn't just being withheld for further analysis, it was being quarantined. They went further, alleging that a limited subset of personnel had been instructed not to refer to the signal in official emails, but to use a placeholder term, echo drift, a code used when discussing signals that may indicate artificial modulation without invoking words like engine or intelligence. Skeptics, of course, immediately dismissed the thread. Anonymous leaks are nothing new, and social media is a breeding ground for elaborate hoaxes. But what set this thread apart was its technical precision. It included details about ESA's internal signal routing, the clock drift error margins in Integral's timestamping software, and even the exact calibration offset used to correct for Earth limb occlusion in gamma ray exposures. In other words, information only someone on the inside would likely know. Within hours, the account was suspended. Archived versions were downloaded and passed around on Reddit, Discord, and even in private astrophysics Slack channels. ESA refused to comment, citing unauthorized digital dissemination of internal operational logs. NASA said nothing at all. But by then, the damage was done. The narrative had changed. What was once seen as a possibly exotic but explainable comet had now acquired a new status, a protected data object. Not because it posed a threat, but because, allegedly, it revealed something we weren't supposed to see. And the most disturbing part, according to the whistleblower, this wasn't the first time, only the first time it was noticed. On August 24, 2025, a team at Hawaii's W.M. Keck Observatory turned one of the most powerful ground-based spectrometers in the world toward 3I-ATLAS. At the time, it was still hundreds of millions of kilometres from the Sun, but already showing strong signs of activity. The team expected to collect basic compositional data, ice content, trace organics, maybe some metal signatures typical of long-period comets. What they found was something far more troubling, a strong, continuous nickel emission line, completely unsupported by iron. In astronomy, certain ratios are sacred. The nickel-to-iron ratio is one of them. It's consistent across stars, planets, meteorites, and comets. That's because both elements are born in the same supernovae, fused in the intense nuclear reactions inside massive stars, expelled during their collapse and seeded equally into the protoplanetary disks from which solar systems form. When you find one, you always find the other. The ratio might vary slightly depending on temperature or local chemistry, but never by much, never like this. Yet 3I-ATLAS was shedding pure nickel, measured at 4 grams per second, with no spectral trace of iron, not even a suppressed signature, nothing. At first, the team assumed a calibration error, perhaps an issue with the spectrometer's filters or signal processing. But after double-checking against reference stars and running a control scan on a known iron-rich asteroid, the anomaly remained. The system was working fine, the data was real, the nickel was real, the iron, somehow, was missing. The implications of this are difficult to overstate. In a natural body, such a separation shouldn't exist. If nickel is being vaporized, iron, which has nearly identical bonding properties and a slightly lower condensation temperature, should also be liberated. In known comets, both metals are detected together in low concentrations, typically embedded in mineral grains that sublimate when heated. That's the standard model. But 3I-ATLAS defied that model. It wasn't just emitting nickel, it was emitting only nickel. There is only one known process that routinely separates nickel from iron, with this level of purity, the Mond process. Developed in the 1890s and still used in advanced metallurgy today, the Mond process involves exposing impure nickel ore to carbon monoxide gas. The nickel reacts to form nickel tetracarbonyl, a volatile, gaseous compound that can be separated, condensed, and thermally decomposed to produce ultra-pure nickel. Iron does not participate in this reaction. It remains behind. This process has never been observed in nature. It requires precise gas ratios, moderate pressures, and a controlled temperature environment. Not something you find drifting through interstellar space. And yet, the spectral fingerprint of 3I-ATLAS's emissions looked suspiciously like nickel tetracarbonyl outgassing. The temperature range matched. The symmetry of the jets, observed extending both toward and away from the Sun, suggested internal pressure rather than solar-driven activity. And critically, the emission was stable, not fluctuating as you'd expect from chaotic cometary vents. Some speculated that maybe the object was shedding metal from surface grains that had nickel, but were naturally depleted in iron. But this too fails to hold up. Even in exotic meteorites, nickel and iron are conjoined. You don't get one without trace elements of the other, unless you engineer it that way. That's what made this so disturbing. The nickel wasn't coming from a messy mixed surface. It was coming from a refined, filtered source, as if 3I-ATLAS had structures or coatings made of high-grade nickel alloys, or worse, as if it was venting the byproduct of a manufacturing process that had begun to fail under solar stress. The data was confirmed in early October by the Very Large Telescope in Chile. Different team, same result: high nickel, zero iron. This isn't how comets behave. This isn't how planets form. This is how machines are built. And something in 3I-ATLAS may be breaking down. On October 15, 2025, amateur astronomers across Europe began to report something strange while tracking 3I-ATLAS. The appearance of a second tail, but not trailing behind the object. Rather, extending forward, pointing directly toward the Sun. This wasn't an imaging artifact. It was visible through wide-field scopes, stacked exposures, and eventually even lower-end DSLRs. As the main dust tail streamed away in the expected direction, pushed outward by solar radiation, a narrow needle-like protrusion jutted in the opposite direction, glowing faintly but unmistakably. What they were seeing was an anti-tail. In cometary science, anti-tails are rare, and when they do appear, they're usually the result of perspective effects. Geometrical illusions created when Earth passes through the orbital plane of a comet, momentarily aligning the dust trail in such a way that part of it appears to project toward the Sun. They are optical, not physical, and they typically last only a few days. But the anti-tail of 3I-ATLAS wasn't following that rule. It appeared earlier than expected, persisted for over 11 days, and crucially, showed different spectral properties than the main dust tail. That was the first real clue that this wasn't just a visual trick. The initial spectral scans from ground-based observatories revealed something unusual. The forward-projecting feature did not reflect sunlight the way dust or ice would. Instead, it emitted faint but detectable ultraviolet and X-ray signatures, indicating either excited plasma or an ionized gas column. That's not something geometry can explain. That's physics. Something was actively producing energy toward the Sun. Even more disturbing were the polarization readings. Normally, cometary tails, especially dust-based ones, scatter sunlight in predictable patterns, allowing scientists to determine their composition and particle size. But the anti-tail showed polarization angles inconsistent with solar backscatter. Instead of diffusing light, it seemed to be refracting and channeling it, like a semi-structured plasma wave aligned along a magnetic axis. By October 20th, NASA's Solar Terrestrial Relations Observatory, STEREO-A, had caught partial imaging of the anomaly from a different perspective. Their onboard imaging system detected a filament-like feature stretching back toward the object, but slightly offset, not directly aligned with its core, but seemingly emitted from a location adjacent to the nucleus. This positional offset hinted at something artificial. Natural anti-tails originate from the same surface area that produces the main coma, but this one was displaced, suggesting either a secondary emission point or something rotating independently near the object. Around this same time, ESA's solar orbiter logged an abrupt spike in ionized nitrogen and carbon particles in the path of the anti-tail, but not in the path of the dust tail. This confirmed it wasn't just reflecting light, it was emitting mass, and that mass was directional, charged, and high energy. Some theorists began speculating that this could be the signature of a magnetic deflection system, similar in concept to early designs of plasma sails or electromagnetic braking used in high-speed spacecraft prototypes. If 3I-ATLAS were interacting with the solar wind in a controlled way, either passively through material design or actively through directed fields, the anti-tail could be a kind of wake, or even a shielded exhaust vector. But perhaps the strangest finding came from infrared imaging. While the dust tail registered normal thermal emissions consistent with fine-grained particles, the anti-tail remained cool, almost too cool. This contradicted every model of solar proximity. Something in or around the antitail was resisting the sun's energy. It's still unclear whether this forward-pointing structure is part of the object, an attached system, or a physical reaction to an unseen field. But what is clear is that it's not dust, not ice, and not normal. For now, scientists are calling it a collimated plasma anomaly, but the term doesn't explain the geometry, or the emission, or why it started exactly as the object began its descent toward perihelion. The tail that points toward the sun shouldn't exist. But with 3I-ATLAS, things that shouldn't exist keep appearing. On October 15, 2025, astronomers began to report an unexpected visual phenomenon trailing from 3I-ATLAS. Not one, but two visible tails. The first behaved as expected, a long arc of dust and ice particles flowing directly away from the sun, shaped by solar radiation and the solar wind. But the second tail defied both geometry and precedent. It pointed forward, toward the sun itself. To the trained eye, this was not just a reflection artifact or a perspective illusion. It was a rare and unsettling structure, a persistent anti-tail, visible across multiple observational bands and increasingly difficult to explain as natural. Anti-tails are not unheard of, but they are usually brief and optical in nature. Illusions caused by Earth passing through a comet's orbital plane, creating the appearance of a forward spike due to geometry. They are temporary, they fade quickly, and they always share the same spectral composition as the main tail, since they're made of the same particles. But the anti-tail from 3I-ATLAS defied all of that. It persisted for over 11 days, sharpened in structure instead of dispersing, and, most significantly, revealed a completely different spectral signature than its dust counterpart. Amateur astronomers using stacked exposures first confirmed the anomaly in visible light, but it was observatories equipped for broader spectra that uncovered the most concerning details. Instruments operating in the ultraviolet range picked up narrow band emissions in the 200-300 nanometer range, consistent with ionized nitrogen and carbon. Meanwhile, X-ray detectors aboard the Solar Terrestrial Relations Observatory, STEREO-A, and ESA's solar orbiter recorded faint emissions consistent with high-energy plasma activity. No natural anti-tail has ever shown such behaviour. More anomalies followed. Polarization studies, techniques used to understand how light interacts with particles, revealed that the anti-tail did not scatter sunlight randomly, like dust does. Instead, it produced coherent polarization vectors, suggesting a semi-ordered structure. In simple terms, the particles in the anti-tail weren't just drifting. They were aligned, possibly shaped by a magnetic field or internal guidance system. The idea that this could be a structured emission rather than a chaotic outflow changed the tone of many discussions happening behind closed doors. By October 20th, NASA's preliminary models could no longer explain the anti-tail through geometry alone. The object's trajectory, solar angle, and phase orientation ruled out the traditional plane-crossing explanation. More curious still, the emission didn't seem to originate from the core of 3I-ATLAS, but slightly offset, suggesting a secondary emission source, possibly rotating. Infrared telescopes scanning for thermal output found that while the dust tail matched the temperature profile of sunlit grains, the anti-tail was exceptionally cool, which made no thermodynamic sense. It seemed to emit light but not heat, a phenomenon that doesn't occur in natural materials at this proximity to the sun. ESA released a brief note, referring to the anomaly as a collimated forward plasma structure, an intentionally vague term suggesting neither natural nor artificial origin. Internally, several researchers began exploring the idea that the anti-tail might be the byproduct of magnetohydrodynamic control, a concept used in some spacecraft propulsion theories, where plasma is steered using magnetic fields. If true, this would mean the object was either interacting with or generating a controlled response to the solar environment. The visual intensity of the anti-tail faded after October 26th, just before 3I-ATLAS reached perihelion. But the mystery deepened. Instruments aboard Earth-orbiting satellites recorded subtle changes in the sun's local magnetic topology, too weak to cause concern but oddly synchronized with the timing of the anti-tail's disappearance. In nature, tails follow. They do not lead. Yet here, 3I-ATLAS defied that rule, and what pointed toward the sun, cool, ionized and aligned, may not have been a tail at all, but a signature. On October 25th, 2025, Just 2 days before perihelion, the Sun released a powerful coronal mass ejection, a high-velocity burst of plasma and magnetic energy that travelled directly through the inner solar system. By itself, that wasn't unusual. The Sun had been particularly active throughout October, with several mid-level M-class flares and intermittent plasma releases. But this CME was different, not in its intensity, but in its trajectory. It wasn't aimed at Earth, Mars, or Venus. It was headed straight for 3I-ATLAS. Initial modelling from NOAA's Space Weather Prediction Centre showed a clean impact vector. The CME was on a direct collision course, with the object's path at approximately 60 km per second, with impact projected around 1940 UTC. Normally, a CME impact on a comet would produce immediate and observable effects, stripping surface material, disrupting magnetic alignment, and causing a flare-up of the coma as volatile particles were violently ejected. That's what scientists expected, but that's not what happened. Telescopes that were tracking 3I-ATLAS in multiple wavelengths, including the Solar Orbiter, Stereo A, and several ground-based observatories, reported no fragmentation, no thermal spike, and no brightening of the coma. There was no increase in dust velocity, no spectral broadening, and no UV spike. In fact, in the minutes following the predicted impact window, the object dimmed. It was as if the CME had passed through the object, or worse, around it. The event confounded researchers. Solar plasma is not subtle. It carries billions of tons of charged particles and can trigger auroras on Earth, disable satellites, and deform magnetic fields. For a comet-like body with no known protective field, the impact should have been destructive, or at the very least, highly visible. Yet 3I-ATLAS remained steady, seemingly unaffected, as if shielded by something unseen. When scientists reviewed the CME in detail using LASCO C2 imagery from the SOHO spacecraft, they noticed something even more bizarre. As the wavefront approached the object's location, the inner arc of the CME appeared to split, not evenly, but asymmetrically, curving around a central void, forming a circular indentation in the plasma front. This void was precisely centred on 3I-ATLAS's coordinates at the time. It was as if the solar plasma had been diverted, magnetically refracted or deflected, by an invisible field surrounding the object. Some proposed that the object might carry a strong natural magnetosphere, but this was immediately dismissed. Comets don't have magnetospheres. They aren't large or dense enough to generate one, especially not interstellar objects with weak gravitational cohesion. Others speculated that perhaps the object's plasma envelope, if it possessed one, reacted electromagnetically with the CME in a unique way. But the shape of the split, the smooth curvature of the deflection, and the lack of downstream turbulence suggested intentional redirection, not passive absorption. As the wave passed and dispersed, 3I-ATLAS resumed its previous light profile, only slightly dimmer. No thermal residue was detected, no high-speed particle ejection followed. The object behaved as if it had never been struck, despite every model confirming that it had. Several agencies quietly flagged the incident for further study. No public reports were released, but leaked internal memos from ESA described the object's response as non-reactive under extreme solar loading. One line, redacted in later versions, called it a possible engineered suppression of photonic and charged particle interference, in other words, a shield. Whatever happened on October 25th wasn't just strange. It contradicted everything physics predicts. A solar storm hit an unshielded object travelling at solar escape velocity, and nothing happened. Unless that object wasn't unshielded, unless it wasn't just a comet. On October 27, 2025, the day 3I-ATLAS reached perihelion, its closest point to the Sun, observatories around the world were primed for a show. As with most comet-like objects, scientists expected a dramatic increase in brightness. This is a well-understood phenomenon. The Sun's heat rapidly energizes a comet's surface, vaporizing volatile compounds and triggering violent outgassing. This, in turn, creates a massive reflective coma, a glowing envelope of dust and gas that can expand for tens of thousands of kilometers and brighten the object by several magnitudes in hours. Instead, 3I-ATLAS dimmed. It didn't fragment, it didn't flare, it didn't eject jets of vapor or expand its coma. The object passed through perihelion quieter than any active body ever recorded under similar conditions. while models predicted a magnitude surge of plus 2.1, enough to be visible with basic backyard equipment, the real-time data showed a decline in visual brightness by 0.8 magnitudes. The object grew darker, smaller, and more opaque. It seemed to absorb light rather than reflect it. This was not a subtle deviation. It was a complete break from known cometary behaviour. Telescopes operating in the infrared range, such as NASA's NEOWISE, observed almost no thermal increase on the sun-facing side of the object. The surface temperature, expected to rise rapidly under intense solar radiation, remained surprisingly stable, never exceeding 172 Kelvin, far below typical values for active comets at perihelion. In the ultraviolet, the signature normally associated with water vapour, specifically the Lyman alpha emission line, was completely absent. Something wasn't reacting, or something was blocking the reaction. Scientists initially considered the possibility of an inert surface, perhaps a rock-like interstellar object without volatiles, similar to Oumuamua. But the coma seen weeks earlier proved this was not a dormant rock. 3I-ATLAS had been active. It had been shedding material, just not here, not now, not when it should have been at its brightest. This led some to explore a more uncomfortable theory. The object wasn't dimming because of natural processes. It was actively suppressing reflection. In short, it might have been altering its optical profile. High-resolution imaging revealed subtle polarization shifts in the object's surface, suggesting that the reflective properties of its outer layer had changed. Instead of scattering sunlight like icy grains or dusty minerals, the light was being absorbed and diffused at sharp angles, a behavior seen in metamaterials designed to reduce detection signatures. In aerospace design, such materials are used in stealth technology to minimize radar and light reflection. A spacecraft approaching a star, if built with this principle, might adjust its outer shell to reduce its thermal and optical visibility, for protection, or for concealment. The drop in brightness wasn't uniform either. It occurred in bands, alternating across the object's surface in predictable intervals, almost like rotating segments or panels. Observers at the Mauna Kea Observatory noted that the dimming occurred in a clockwise cycle, consistent with a slow rotational period, possibly indicating engineered symmetry, rather than a random tumbling body. Most alarming of all was the timing. The light curve suppression began almost exactly 4 hours before perihelion and ended 4 hours after. The curve was smooth, deliberate, and centered precisely on the sun's closest approach. This wasn't thermal lag or observational error. This was calculated attenuation. No dust, no gas, no outburst. Just silence, shadow, and motion that didn't match the sun's expectations. To date, no natural body has ever dimmed during perihelion, after previously showing activity, except this one. 3I-ATLAS should have lit up the sky. Instead, it dimmed, and in that dimness something hid itself, right in front of the brightest object in the solar system. In the early hours of October 28, 2025, just one day after 3I-ATLAS passed perihelion, a small group of researchers at the Jicamarca Radio Observatory in Peru conducted what was supposed to be a routine ionospheric calibration run. Their goal was to measure electron density fluctuations in Earth's upper atmosphere, something they did almost daily using high-frequency radar pulses. But this time, something unexpected came back. The signal bounced. Not off the ionosphere, but off something else, somewhere well beyond Earth's atmosphere. The reflected return didn't match standard delay profiles. It arrived with a time discrepancy of 2.3 milliseconds, suggesting the radar signal had travelled far beyond the expected altitude and returned from a transient object, one not in geostationary orbit or on a known satellite path. At first, they suspected an echo off space debris or an unknown satellite module, but orbital databases returned nothing in the region. The signal return was broad, curved, and scattered across a narrow frequency band, with phase interference consistent with a structured surface. That was when one of the researchers cross-referenced its projected coordinates and found that the return had originated from the same heliocentric vector where 3I-ATLAS was expected to be during its outbound leg. Out of curiosity, and increasingly concern, the team repeated the test. Instead of simply observing the ionosphere, they aimed the array toward the object's calculated path. Over the next 4 hours, they transmitted 78 pulse sequences into the high atmosphere at narrow intervals. 9 bounced back, Each return was distorted but consistent. They were not reflections of atmospheric turbulence or meteor trails. These were hard reflections, the kind that only happen when a high-frequency radar pulse strikes a physical boundary in space dense enough and structured enough to scatter energy back to Earth. What made the event even more unusual was the polarization inversion in the returned signals. Under normal conditions, radar pulses maintain orientation unless disturbed by strong magnetic fields. In all 9 successful returns, the polarization came back flipped, reversed in a pattern consistent with engineered deflection, materials like those used in certain types of stealth coatings. Radar specialists at Jickamaka had seen nothing like it. They sent the raw data to colleagues at the HARP facility in Alaska, who ran the signal through reconstruction software. The result wasn't a coherent image, it was more of a diffraction pattern. But embedded within that pattern was clear indication of geometric curvature, almost like panels or layered surfaces reflecting the pulse unevenly. The returns also showed motion. Between the first and last confirmed echoes there was a measurable angular drift in the reflection boundary, about 0.7 arc minutes, consistent with an object slowly rotating along its own axis. That axis didn't match the previously assumed tumble seen from Earth. It hinted at stabilized rotation, something only achievable through internal correction or design. The team compiled their findings in a confidential report sent to the International Space Environment Service, ISES, labeling the anomaly as multi-bounce radar reflection off a non-atmospheric transient body. The document was flagged for further study, but within 48 hours the Jickamaka system logs were remotely wiped during a firmware patch pushed from an upstream update server. The team had backups, but the timing raised eyebrows. What started as a routine ionospheric measurement ended with a verified signal echo from a supposedly inert interstellar object. In radar terms, it shouldn't have been possible, but it happened. A body that shouldn't reflect radar just did. And if it reflects radar, it's not just ice and dust, it's structured, and someone, or something, made it that way. At 03:14 UTC on October 29, 2025, an unannounced update appeared in the Minor Planet Center's private access feed, viewable only to a network of verified observatories and planetary defense partners. Buried deep in the log data was a seemingly routine entry. Solution reference 53. Trajectory Maintenance Update. The object in question. 3I-ATLAS. The change wasn't in position, but in classification. From that moment forward, 3I-ATLAS was no longer flagged under its usual identifier as an interstellar comet. It had been moved, silently and without formal notice, into the ION watch list. The International Asteroid Warning Network is the backbone of global planetary defense. It's not just a database, it's a real-time alerting system connecting NASA, ESA, JAXA, and dozens of other agencies tasked with identifying and mitigating celestial threats to Earth. And its criteria for inclusion are strict. Only objects that pose a future impact risk, display anomalous trajectory behaviour, or demonstrate unpredictable orbital mechanics are added. 3I-ATLAS now met all 3. This wasn't a public announcement, no press release followed, but the internal alert was echoed across systems in less than 30 minutes. Terminals inside ESA's SSA NEO Coordination Centre in Italy received the signal and forwarded the new classification to their internal command dashboard. In Maryland, NASA's PDCO, the Planetary Defense Coordination Office, logged the update and issued a silent cascade alert to its automated observatories. Within hours, 3 of the world's most powerful optical tracking arrays, Pan-STARRS, Atlas Haleakala, and Matt Lemon Survey, reoriented to reacquire 3I-ATLAS's outbound trajectory. This wasn't a coincidence. These were priority tracking facilities, usually reserved for rapidly approaching impactors, but now they were focused on something leaving the inner solar system. What prompted the change? Sources close to the JPL navigation team suggest the tipping point wasn't any one event, but a pattern. In the 6 days surrounding perihelion, 3I-ATLAS had deviated from its predicted path 11 separate times, each within a variance window that exceeded standard gravitational perturbation allowances. Tiny shifts, arcsecond level, but consistent, almost rhythmic. Then came the LASCO CME split, then the non-brightening at perihelion, then the bounce signal. Each anomaly alone could be rationalized, but together they formed a chain, and that chain triggered protocol escalation. In response, NASA activated its Near-Earth Object Confirmation page, NEOCP, monitoring script for 3I-ATLAS, but behind a firewall, hidden from public view. Normally used for candidate impactors, the script allows for minute-by-minute orbital refinements using data from dozens of international facilities. The feed was tagged Non-Impact, Non-Terrestrial Influence Suspected, a label that had never appeared in the database before. Privately, members of the IABN advisory group began questioning whether 3I-ATLAS still qualified as a natural object. Not because of its origin — interstellar visitors are rare but not unprecedented — but because of its behaviour. It moved like a comet, but not quite. It responded to solar plasma like no comet should. And now, post-perihelion, it was maintaining an outbound velocity profile inconsistent with deceleration from solar gravity. This wasn't a body falling back into deep space. It was navigating out of it. By late October 29th, new data from ESA's 3I telescope in Sicily detected minor microfluctuations in the object's brightness. Not enough to be visible to the human eye, but clear under stacked exposures. The frequency of these pulses matched the object's previously estimated rotational period, suggesting coordinated surface adjustments. For the first time, the term intentional activity appeared in an internal annotation, not in a report, in a caution tag, added by a senior analyst, then removed 40 minutes later. But it was there. And now, so is the world's most powerful planetary defense system. Watching. Quietly. Closely. At 0442 UTC on October 30th, 2025, observers attempting to access the Small Body Database Lookup tool on NASA's Jet Propulsion Laboratory website encountered something unusual. When searching for 3I-ATLAS, the response didn't return a typical data page. Instead, users were redirected to a generic message. Object registration currently undergoing review. Data temporarily unavailable. This had never happened before. For decades, the Small Body Database has been open to the public. Even objects under active monitoring, including potentially hazardous asteroids, remain visible for transparency and public trust. Yet now, one of the most tracked objects in the solar system, an interstellar visitor flagged by IABN, was suddenly locked behind a firewall. Within hours, other systems followed. The Horizon's Ephemeris service, normally used by astronomers to pull live trajectory predictions, blocked queries for the object's designator. The Minor Planet Center's observation logs, which typically show every official astrometric point submitted by global observatories, showed blank entries for 3I-ATLAS past October 29th. No explanation, no public notice. It was as if the object had been quietly erased. This wasn't a glitch. It was intentional containment. The first clue came from an internal memo leaked by an engineer at the European Space Operations Centre, ESOC. The memo referenced a protocol update labelled Sentry Hold Quiv 4.6, a rarely invoked data isolation directive meant to limit the distribution of observational data when the target is either 1. Undergoing active governmental review, or 2. Suspected to involve non-gravitational behaviour of unknown origin. That same morning, developers monitoring GitHub noticed that NASA's public-facing tools had received a silent patch, one that introduced conditional query suppression based on object flags. The commit comment simply read, "Temporarily exclude flagged foreign body designators until review status lifted." The object had been digitally sealed. Researchers around the world scrambled to understand why. Many had been running automated data pools to model 3I-ATLAS's trajectory and brightness evolution. When those scripts failed, it didn't just break research pipelines, it set off alarms. Planetary scientists in Japan, Chile and Germany reported simultaneous loss of access. No other object was affected. But perhaps the most telling change came from ESA's Open Science portal. The agency hosts thousands of gigabytes of observational data, including real-time feeds from missions like Solar Orbiter and Bepi Colombo. As of October 30th, any datasets containing direct imaging of 3I-ATLAS had been pulled or redacted. In place of thumbnails or spectral files were placeholder messages. Frame withheld pending validation. The reasoning given? Quality control. But behind the scenes, internal access logs showed that download permissions were disabled manually, not algorithmically. Several dataset folders were renamed with classification flags typically reserved for government-reviewed content, Not military, not sensitive, just withheld. Astronomers with pre-existing local archives began to compare notes. The last publicly available orbital solution, released on October 28th, showed the object on a hyperbolic escape path. But amateur reconstructions using archived frames showed a faint deviation beginning October 29th, consistent with a minor thrust or delta V. The angle was small, less than 0.1 degrees, but real. Then the systems locked. No new frames, no new orbital updates, no more access. At face value, the move contradicted every principle of open science. But to those watching closely, it suggested one thing: control. The data had become too unusual, too layered, too hard to explain within the language of natural phenomena. And before the questions could spread, the systems that fed them were quietly unplugged. What was once open is now hidden. Registration closed, access locked, and behind that lock, something Earth's institutions weren't ready to explain. At 09:17 UTC on October 30th, 2025, an internal command was uploaded to ESA's JUICE spacecraft, short for Jupiter Icy Moons Explorer, currently en route through the inner solar system on its long journey to the Jovian system. The maneuver, logged in ESA's Internal Operations Registry under update tag DV017 AU Delta, was listed as a minor vector correction. But those watching closely saw something else. JUICE had just been redirected. The JUICE mission was never intended to study interstellar comets. Its objectives were clear: detailed exploration of Jupiter's icy moons, including Ganymede, Europa and Callisto. Launched in 2023, it had been performing routine gravity assists and deep space calibrations, waiting for its 2029 arrival at Jupiter. The current cruise phase was supposed to be quiet, boring even. Yet on October 30th, JUICE initiated a planned roll and orientation hold. Then, over a 2-hour window, it executed 3 microbursts from its attitude control thrusters, nudging the spacecraft just enough to change its line of sight. The new alignment, a point in space approximately 4 million kilometers ahead of 3I-ATLAS's outbound path. This was not a navigation error. The maneuver was precise and clearly designed to put JUICE in a cross-observational position, allowing its Janus optical camera system and UVS spectrometer to perform passive imaging as 3I-ATLAS passed by at an angle. It was an intentional decision to track the object, even though the mission had no formal directive to do so. ESA made no announcement, no press release, but amateur trackers noticed that JUICE's trajectory had shifted slightly on publicly available ephemeris maps. By October 31st, the spacecraft was now on a slightly altered path that would allow it to intersect the object's forward shadow cone, the region where its interaction with solar light would be most observable from behind. Why risk the adjustment? Internally, a brief mention appeared in a restricted bulletin from ESA's Planetary Science Archive. Opportunity window for outbound spectral sweep of unidentified heliocentric transient. Observation non-invasive, passive only. The wording was careful, avoiding the term interstellar, avoiding comet. The object was now a transient, but the implications were clear. JUICE, a €1 billion mission designed for the moons of Jupiter, had just been retasked mid-mission to aim at something passing through the inner solar system, something that, by all public accounts, had already been declassified from open databases, something Earth-based systems were no longer allowed to image. The spacecraft's onboard sensors aren't designed for comet analysis, but they are capable. The Janus camera has enough resolution to detect coma structures, tail alignments, and surface brightness irregularities at long range. The MAGIS instrument, a near-infrared hyperspectral mapper, could detect trace elements of water, ammonia, or synthetic compounds. Even passive observation could be revealing, and that's what made the redirect so significant. JUICE wasn't being sent to intercept 3I-ATLAS. It was being positioned to observe from a safe distance, in a band where other instruments couldn't see. From behind, away from Earth, where reflection, phase behaviour, and non-visible emissions could be measured without interference from solar scattering. It was the equivalent of placing a security camera behind a locked door, quiet, watchful, unspoken. To this day, ESA has not acknowledged the maneuver publicly, but the telemetry is clear. JUICE was moved, And the only thing in that new field of view was 3I-ATLAS. A spacecraft bound for Jupiter is now watching a comet that shouldn't be here, because someone decided it was worth watching. At 01:11 UTC on October 31st, 2025, the Allen Telescope Array in Northern California began a scheduled sweep across a narrow sky segment, one that included the outbound path of 3I-ATLAS. The scan was part of a long-running protocol from the Search for Extraterrestrial Intelligence, SETI, Institute, routine broadband monitoring of fast-moving solar system objects as they transit out of Earth's observational range. Most of these sweeps are symbolic, exercises in due diligence, not expectation. But this time, something different happened. Or rather, didn't happen. SETI's dynamic spectral range covers the 1 to 10 GHz window, also known as the water hole, frequency range between the emission lines of hydrogen and hydroxyl where cosmic noise is lowest. If intelligent signals were to be sent, this is where they'd likely appear. Comets, meteors, and asteroids don't emit in this band. The scans are almost always silent. But 3I-ATLAS gave back something more unusual than noise. Absolute silence. Across all channels, all frequencies, all fallback bands. No radiation, spikes, no harmonics. Not even background cosmic noise. It was a frequency void. This might not seem strange, until you realise what should have been there. As 3I-ATLAS moved outbound past perihelion, its trajectory placed it between Earth and a strong radio source in the galactic plane. Even without the object emitting anything, it should have caused diffraction artifacts, Doppler lensing, or partial reflection of natural background emissions, like every other known object does when it moves across that same band. Instead, the waveform returned from the Allen array showed zero interference. It was as if something had swallowed the noise. The SETI team rechecked the calibration. Instruments were fine. They rescanned the same section of sky an hour later. No difference. Then they did something unprecedented. They rescanned the same corridor 5 more times over the next 24 hours, using varied antenna configurations and fallback telemetry from other partner facilities, including the Green Bank Telescope in West Virginia and Meerkat in South Africa. Each sweep returned the same anomaly. Perfect spectral silence centered precisely on the moving coordinates of 3I-ATLAS. By November 1st, SETI's internal logs began to list the object as an interference null, not because it was jamming anything, but because it produced an acoustic shadow, a dead zone where background frequencies disappeared when the object passed in front of distant sources. No passive body, especially one made of dust and ice, has ever behaved this way. Some researchers theorized a form of active absorption, a technology that could, in theory, flatten inbound signals by tuning surface structures at the atomic level. In military aerospace design, this would be the equivalent of broadband stealth, not just invisible to radar, but invisible to space itself. This hypothesis remained locked in SETI's private forum, tagged speculative anomaly, no disclosure. But the debate intensified when one signal analyst noted a strange pattern. Each time the void passed through a high emission background source, there was a fractional time lag in the reappearance of those frequencies, as if something had absorbed and re-emitted the signal after a brief delay. It was never confirmed. The data was incomplete, but the silence wasn't, and that silence began to ripple. On November the 2nd, the SETI Institute temporarily suspended public access to its live signal archive, citing maintenance, even though the servers were healthy. The scan data was removed from public view. A final note appeared internally. Frequency absence confirmed. No explanation consistent with natural occlusion. In the vastness of space, noise is normal, static is the rule, but 3I-ATLAS didn't echo, it erased. And that kind of silence is harder to explain than a signal. On the night of November the 2nd, 2025, a group of amateur astronomers in southern Spain gathered for a routine deep sky observation session. The group, known locally as La Palma Skywatchers, had no connection to space agencies or academic institutions. They weren't looking for anomalies. They were simply tracking what many thought to be the most mysterious object of the year, 3I-ATLAS. At 21:43 local time, using a modest 11-inch Schmidt-Cassegrain telescope and a CCD camera rigged for long exposure, the group began capturing stacked frames of the object's projected position. Their intent was to capture motion blur trails for analysis, the kind of astrophotography popular in amateur circles. What they recorded instead sparked a wave of attention across private observatories. In a span of 6 frames, each separated by 45 seconds, the object showed a steady, predictable drift, until the 3rd frame. In that exposure, 3I-ATLAS was gone, not dimmed, not blurred, gone. Then, in the 4th frame, 45 seconds later, it was back, perfectly aligned with its predicted track. This wasn't equipment failure. The stars in the frame remained sharp. The background galaxies remained visible. The guide star calibration was untouched. There were no clouds, no power interruptions, no vibration spikes. Just one missing object for one frame. The group posted their results to a public astrophotography forum. Within hours, amateur astronomers across Europe and North Africa began checking their logs. And what they found was stunning. Multiple independent captures, all showing the same blink, a disappearance, a reappearance, roughly 45 seconds apart. By November 3rd, private observatories in Austria, Tunisia and Cyprus had confirmed similar observations. Some used different equipment, some captured the blink at slightly different intervals. But they all had one thing in common. 3I-ATLAS briefly vanished from the optical spectrum. This was no ordinary fluctuation. Natural objects don't blink. Even fast rotators with albedo variation, like asteroid 3200 Phaethon, never fully disappear in a single frame. Light curves vary, shadows shift, but complete photometric occlusion is unheard of unless an object physically passes behind another, or actively obscures itself. Theoretical astrophysicists offered 2 possibilities. The first, the object's surface may contain photochromatic elements, materials that change reflectivity under specific solar conditions. If the object's rotation exposed a panel or face with unusually high absorption characteristics, it could theoretically vanish from visible light under certain angles. But for that to happen in multiple independent observations, all within the same 60-second window, the rotation would have to be engineered, not random. The second possibility was more speculative, a localized energy discharge or shielding effect that briefly refracted or bent light away from the observer's line of sight. This could explain the 45-second window, not as an absence, but as a redirected path. In simpler terms, the ray object didn't disappear, the light from it never reached Earth. And then came the strangest report of all. A private observatory in Morocco, running a custom-built near-infrared array, reported an inverse flash. Just as the object vanished from the visible spectrum, it registered a brief spike in the 817 nanometer band. Not visible to the human eye, but consistent with low-frequency emissions from heated surfaces or energy transitions. It was only detectable in one frame. One blink. Just enough to raise questions. Not enough to answer them. No agency responded to the amateur posts. No public database recorded the anomaly, but across scattered forums and email lists, a single idea was whispered. 3I-ATLAS didn't disappear. It hid. By November 3rd, 2025, astronomers around the globe were focused on one question. Why was 3I-ATLAS's brightness no longer following any predictable pattern? Comets, even interstellar ones, obey certain photometric rules. As they approach the Sun, their brightness increases in accordance with the inverse square law. More sunlight equals more vaporized material, equals more reflective dust. Then, as they recede, they gradually fade. Models can forecast this behavior with high accuracy. But 3I-ATLAS broke the curve. Again, it started subtly. After its perihelion pass, most observatories expected the object to dim steadily. Instead, between October 30th and November 3rd, brightness values fluctuated by as much as 0.9 magnitudes, not randomly, but with a gentle undulating pattern. This drift wasn't just seen from one place. It was confirmed by the Canada-France-Hawaii telescope, ESO's La Silla Observatory, and even amateur trackers with access to high-frame stacking algorithms. Night after night, the object's apparent brightness would increase slightly, plateau, then decline, before repeating again. Not fast, not dramatic, but consistent, and completely unexplained. Initial theories blamed viewing angle, the idea that surface reflection was varying as the object rotated, but spectrographs showed no corresponding change in coma density, tail structure, or dust production. In other words, the object wasn't reflecting more light, it was either emitting it or modulating what we saw. That's when researchers dug deeper. Using time series photometry, they overlaid the brightness drift pattern onto the object's estimated rotation period. If it was spinning irregularly or tumbling chaotically, the peaks would align with changes in exposed surface area, but they didn't. Instead, the brightness drifts followed a smoother, broader cycle, nearly 3 hours long, completely decoupled from any known spin rate. This suggested something far more complex: a pulsed luminosity envelope, a phenomenon never observed in natural cometary bodies. Some speculated internal activity, perhaps heat pockets triggering delayed outgassing from within the nucleus. But once again, thermal readings from infrared. Telescopes didn't support this. The surface temperature of 3I-ATLAS remained abnormally stable and unusually cold, with no thermal spikes to match the optical pulses. Others proposed a more radical idea: external light modulation. If the object had a thin, possibly ionized envelope, something like a plasma sheath, its appearance could shift subtly depending on how it interacted with solar radiation or charged particles. This could explain brightness without thermal variation. But to maintain such stability across multiple days and latitudes, that required active regulation, a boundary condition being maintained across multiple cycles, not just a random flicker of space dust. And then came a quiet admission. A university research group in Belgium, working independently, found that the brightness drift pattern, when translated into frequency space, produced a repeating harmonic signature. 3 distinct wave peaks emerged. All were spaced with near-perfect ratios of 2.35, the foundation of Fibonacci symmetry, often seen in natural systems like spirals, galaxies and shells, but not in comets, not in something tumbling through space at 60 kilometers per second. The group called it aesthetic noise, a signal pattern that suggested design, or at the very least constraint. They didn't claim artificiality, but they quietly noted: natural photometric variability does not typically produce harmonic distribution in light curve analysis. So what causes an object to brighten and dim without outgassing, without thermal change, and without impact? Nothing we've observed before. The brightness wasn't random, it wasn't solar, and it wasn't fading. It was drifting, like a pulse, like a timed loop, and whatever was inside that loop was not in a hurry to leave. On November 4th, 2025, researchers operating the Gran Telescopio Canarias on La Palma performed a high-resolution spectral sweep of 3I-ATLAS, targeting the 630.0 to 636.0 nanometer range, the window where atomic oxygen emissions are most reliably detected in space. This is a standard practice when studying comets, especially as they pass close to the Sun. Solar radiation often excites molecular oxygen in the coma, producing well-understood spectral lines. But this time, the oxygen line didn't show up as expected. Instead of a clear, narrow emission spike near 630.2 nanometers, the spectrum revealed a gap, a clean absence where the line should have been. Not a blur, not a noise artifact, a sharp dip, as if something had filtered that specific frequency out of the returning light. The team ran the test 3 more times across multiple instruments. The anomaly remained. And it wasn't just limited to 630.2. Additional dips appeared at 636.3 and 634.7 nanometers, both sublines often associated with neutral oxygen fragments. The gaps were sharp-edged, symmetrical, and cleanly isolated. They weren't caused by instrumentation limits or atmospheric distortion. This was a signature produced in space by the object itself. To understand why this was so strange, it's important to recognize that oxygen lines are universal. Whether in diffuse gas clouds, comet tails, or even Earth's own upper atmosphere, they appear reliably, a direct result of sunlight interacting with oxygen-bearing molecules. But here, those frequencies were missing, filtered, blocked, silenced. One theory posited an intervening cloud of charged particles, perhaps a local sheath around the object that absorbed or refracted light in narrow bands. But to target only oxygen lines, and do so cleanly across different wavelengths, would require a precision rarely seen in natural systems. That's when a second team, working independently at the Subaru telescope in Hawaii, submitted their own observations. They too had scanned the oxygen band on November 3rd and confirmed the same pattern: 3 spectral voids spaced precisely across the red band. But what caught their attention was what replaced the missing oxygen signal. Instead of the expected spike at 630.2, The Subaru team recorded a slight rise in neighbouring bands, like energy being redistributed away from the blocked lines. This wasn't standard absorption, it was selective suppression. In physical terms, it resembled active filtering, a process by which certain frequencies are absorbed or deflected while others are allowed through. In Earth-based optics, this is achieved with narrowband filters made of layered glass or coated metal films, used in everything from telescopes to stealth technology. In space, no known natural process performs this function at such tight bandwidths. The idea that 3I-ATLAS was surrounded by a frequency-selective envelope began to gain traction. And then came the strangest coincidence. In signal processing labs, the 636 nanometer band is known for another use, optical communication. Specifically, free space laser transmission systems, the kind used in inter-satellite links and deep space probes, often avoid these lines to minimize interference. These systems are programmed to skip certain atmospheric absorption bands, including the exact gaps now seen in 3I-ATLAS. It led some to speculate. Was the object shielding these lines to prevent detection? Or was it using that band for something else entirely? No agency made an official statement, but on November 5th, both observation teams were instructed to reroute their proposals for further review. Their raw data was still available, but access had been flagged. The gaps in the oxygen band weren't random, they were patterned, they were clean, and they matched no comet ever recorded. What's missing in the light spectrum can often say more than what's there. On October 25, 2025, 3 powerful coronal mass ejections, CMEs, erupted from the Sun in rapid succession. Each was tracked by NASA's SOHO spacecraft, the Stereo Ahead, observatory and ground-based coronagraphs. What made this event different was their direction. All 3 plasma waves converged toward the exact outbound trajectory of 3I-ATLAS. This alignment was rare. According to heliophysics models, the object was directly in the path of impact. At least one of the CME shock fronts should have struck it with enough force to disturb the coma, dislodge surface material, or, at the very least, scatter debris into a visible dispersion trail. But it didn't. Instead, what followed was a non-event, a silence, and then a mystery. Multiple observatories, including Mauna Kea, Lucia, and Pan-STARRS, began watching the object closely in the days that followed. They looked for expected signs: expansion of the dust cloud, fragmentation of smaller bodies, thermal spikes from sudden solar exposure, anything that would suggest the comet had reacted. But 3I-ATLAS remained unchanged. Its coma stayed symmetrical, its core structure showed no visible fracturing. And perhaps most critically, there was no debris field. Normally, when a CME hits a cometary body, the energy causes volatile material to erupt from the surface. Even small impacts create microparticle trails that scatter sunlight and glow faintly in post-strike observations. But when ESA's solar orbiter captured images 3 hours after the final CME passed through 3I-ATLAS's corridor, the region behind the object was clean, not dim, not sparse, empty. Researchers were stunned. In past solar interactions, like the 2011 CME impact with Comet Lovejoy, the tail length increased dramatically, and fragmentation occurred within hours. In contrast, 3I-ATLAS appeared to have absorbed the CME energy with no visible reaction. It didn't flare, it didn't rotate, it didn't even flicker. This prompted a deeper analysis. NASA's Heliophysics Systems Observatory ran simulations to model the impact profile. The CME's density and velocity were high enough that even a small asteroid should have shown measurable deflection. But 3I-ATLAS maintained its course to within 0.0001 arc-seconds. No deviation, no measurable momentum exchange, as if the wave had passed through it, or had been somehow diverted. Some theorized that the object was shielded by an electromagnetic envelope, a kind of natural magnetosphere that deflected plasma in the way Earth's magnetic field protects us from solar storms. But for an icy interstellar body to generate that kind of field, it would require active internal energy, sustained over time. Other experts pointed to the plasma shadow, a thin, trailing region behind the object where ionized particles were expected to scatter. Observations from the TRACE satellite revealed that this zone was narrower than any natural comet ever recorded, just 0.2 degrees wide and sharply defined, as if the CME had been channeled or redirected rather than absorbed. Then came the radar scans. ESA's Goldstone Deep Space Complex attempted to bounce long-wave radar off the object's trajectory zone, hoping to detect dust dispersal. The return signal showed a clean silhouette, no residual echo, no expanding fragments, no trailing debris. It was as if the object had never been touched. This wasn't just unusual, it was unprecedented. If the CME had missed, the models were wrong. If it had hit, then 3I-ATLAS had somehow neutralized the blow. Without movement, without heat, and without leaving behind a single piece of itself, no fragments, no ejecta, no scars. A solar storm passed through space, and space, around 3I-ATLAS, simply folded in silence. At 05:06 UTC on November 6, 2025, a quiet update appeared on NASA's JPL Horizon system, the tool responsible for calculating and distributing the orbital paths of thousands of solar system objects. Without announcement, the trajectory model for 3I-ATLAS was marked as updated with revised residuals. To the casual observer, this meant nothing, but to astronomers, that phrase carried weight. It meant the math had changed, and it wasn't a small correction. For over 4 months, the path of 3I-ATLAS had followed a clear hyperbolic arc, one consistent with an object entering the solar system from deep interstellar space. Early estimates predicted it would slingshot past the Sun and exit on a clean outbound vector, never to return. Its high eccentricity and lack of gravitational binding made it a textbook non-recurring visitor. But the revised model showed something different, something that shouldn't have been possible under Newtonian mechanics alone. The new orbital solution included a non-gravitational parameter, a term typically reserved for cometary outgassing or other asymmetric forces acting on the body. In practice, this suggested that 3I-ATLAS had either changed speed, changed direction, or both. Not drastically, but enough that the entire outbound trajectory now missed its original target corridor by nearly 400,000 kilometers. That's the distance between Earth and the Moon. And it happened in silence. Astrometric data from ground-based telescopes confirmed the shift. Independent tracking logs submitted to the Minor Planet Center showed a consistent deviation from predicted values starting October 29th, just after the perihelion phase and shortly before the CME encounters. The object was no longer matching the forecasted coordinates. It was drifting, slightly but persistently. One possible explanation: outgassing. Comets often shed material as they heat up, releasing jets of gas and dust that can act like tiny thrusters, pushing the object off course. But thermal imaging of 3I-ATLAS showed no such activity. No fan-shaped emissions, no coma expansion, no asymmetric tail formation. Even the surface temperature remained too low to suggest volatile release. Then what was causing the deviation? That question became more urgent when a second anomaly appeared in the updated JPL model. The time of perihelion had been retroactively adjusted by 67 seconds. This might seem insignificant, but orbital physics is exacting. A full minute of unaccounted drift requires a cause, either a sudden change in velocity or a complex gravitational interaction. Yet there were no planetary bodies close enough to influence the object, no asteroids, no moons, nothing to explain the deviation, unless the object had altered itself. Orbital deviation without visible thrust is rare, but in past deep space missions, spacecraft have used low-thrust propulsion systems, such as ion drives or electric sails, to gently shift trajectories over time, imperceptible in the moment, but decisive over weeks. For a natural object to show a similar behaviour, without mass shedding, without thermal signatures and without optical flare-ups, suggests one of two things. Our physics is incomplete. The object is not behaving naturally. By November 7th, both ESA and NASA had marked the object's outbound trajectory as under observation, a designation typically reserved for bodies exhibiting anomalous orbital elements. And the forecast? Previously, 3I-ATLAS was set to exit the solar system cleanly by mid-2026. Now, its course brings it within close approach of Mars orbit again, just 11 months from now. A return window, not planned, not predicted, but now calculated. The question isn't just where 3I-ATLAS is going, it's why it changed course, and when it decided to. When 3I-ATLAS made its flyby past Mars on October 14th, 2025, planetary scientists expected the event to be rich in observational data. After all, No known interstellar object had ever passed so closely to the red planet, and Mars is not poorly equipped. As of October, 8 operational spacecraft were actively observing Mars: NASA's Mars Reconnaissance Orbiter, MAVEN, ESA's Mars Express, the Trace Gas Orbiter, China's Tianwen-1, and 3 functional rovers with upward-facing cameras. Together, this flotilla offers a continuous, overlapping view of Mars's upper atmosphere and its orbital vicinity. So when 3I-ATLAS passed within 11 million kilometres of Mars, close enough to be seen with wide-angle instruments, the expectation was clear. We would have imagery, we would have spectral data, we would have magnetic field measurements and ionospheric interactions. But when researchers went looking for the records, they found nothing. Public access logs from NASA's Planetary Data System show routine uploads of imaging data from MAVEN's Imaging Ultraviolet Spectrograph, IUVS, almost every day throughout October. But between October 13th and 15th, the archive shows a blank record. No files, no frames, just a gap marked only with the word pending. MRO's high-rise camera was scheduled for a high-resolution scan on October 14th, a window that, coincidentally, overlapped with 3I-ATLAS's closest pass. But that sequence was later cancelled, according to mission logs, due to a software timing discrepancy. Even the Trace Gas Orbiter, which had been operating on an automated scan routine for nearly 400 sols, showed an unexpected instrument hold that lasted for 7.5 hours, precisely during the object's projected crossing time. When ESA was asked about the gap, they replied with a templated statement. No anomalies were detected. Observation sequences were reprioritised for seasonal atmospheric studies. Yet the timing aligned too perfectly. It wasn't just the imaging data. Telemetry from Mars's magnetosphere, gathered by MAVEN, also showed a break. A flat line in readings for the ion density and magnetic flux during a 2-hour window. This was not flagged as a system error. The data was simply missing. At first, many assumed it was a transmission delay, but by November 5th, the expectation that delayed logs would appear had faded. The silence was no longer technical, it was deliberate. Private researchers tracking archived satellite logs noticed another anomaly. ESA's Mars Express had activated its Mars instrument, a radio science experiment normally used for atmospheric sounding, but recorded no outbound frequency data during the flyby window. Instead, the transmission log shows an entry labelled passive hold. This designation is used when a spacecraft listens but chooses not to transmit. Listening, but not recording. Flying, but not watching. This stands in stark contrast to how Mars missions behave during unusual events. During past meteor storms, auroral pulses, or solar activity, instruments were reoriented and overclocked to capture every available data point. So why the silence now? One possibility is that the agencies were ordered not to release the data. Another is that they did record something, but it didn't fit any known category. A third, more unnerving theory. The object triggered automated safeties within observational instruments, either through electromagnetic interference or by emitting a signal that mimicked command protocols. Some observers point to the timing of the Mars data gap and the CME convergence just days later. Could the object have been preparing? Could it have masked itself from sensors during this key phase? We don't know, because when the most instrumented planet in the solar system had a front-row seat to an interstellar visitor, the result was silence. Not noise, not static, just empty frames. And sometimes the silence says more than the signal. Every solid body in space rotates, whether slowly like Pluto or rapidly like asteroid 3200 Phaethon. The physics is consistent. Objects conserve angular momentum from their formation or from collisions over time. And when a body moves through the solar system, especially one shedding mass or interacting with solar radiation, its rotation period becomes one of the first measurable parameters. But 3I-ATLAS isn't behaving like a body with angular momentum, because since its discovery, it has shown no measurable spin. Not once, not at all. Early observations in late September 2025 suggested the object was elongated, with a nucleus that, under magnification, appeared slightly oblong. Typically, such shapes produce brightness variations as the object tumbles or spins. These variations are tracked via light curves, where periodic brightening and dimming reveal the object's rotation. But the light curve for 3I-ATLAS has remained flat. No variation, no modulation, a near-perfect constant brightness, even under multi-band scrutiny. Initially, some researchers believed the viewing angle might explain it. If Earth was aligned perfectly with the object's rotational pole, we might see minimal fluctuation, but orbital mechanics quickly ruled that out. As 3I-ATLAS moved past perihelion and changed phase angles with respect to Earth and the Sun, any rotational axis should have tilted relative to our line of sight. Yet the brightness stayed the same. No spin signature, no angular shift, just stability. By November 6th, observatories at Palomar, Kitt Peak and La Palma had all published datasets confirming the anomaly. 3I-ATLAS did not display any identifiable rotational period, not in optical, infrared or radar-reflected light. Even more puzzling, radar scans from the Goldstone Deep Space Network showed a return echo consistent with a non-rotating scatter surface. Typically, rotating bodies produce Doppler shifts in radar reflections, one side moving toward the antenna, the other receding. These shifts allow scientists to model surface shape and spin rate, but the radar signature from 3I-ATLAS was static, no spread, no drift, just a single, unmodulated bounce. One hypothesis emerged: the object might be tumbling extremely slowly, on a timescale of days or weeks. But this conflicts with its environment. As a comet-like body approaches the Sun, surface sublimation typically induces spin-up. Uneven jets of gas act like miniature thrusters. Yet 3I-ATLAS has shown no such acceleration, no torque effects, and, critically, no tail wobble. Its ion tail, in fact, is one of the most geometrically stable structures ever recorded. It points directly away from the Sun with near-perfect linearity, frame after frame. This raised another theory. What if the object isn't rotating, because it's actively stabilizing itself? Spacecraft use gyroscopes, flywheels, and micro-thrusters to maintain fixed orientations. Could 3I-ATLAS be doing something similar, either by internal mass redistribution or through electromagnetic interaction with the solar wind? Such mechanisms aren't theoretical. Human-made probes like Voyager, Pioneer, and OSIRIS-REx have employed spin stabilization or active attitude control. But those are known, engineered systems. 3I-ATLAS, by every public metric, is supposed to be a natural object, and yet its behaviour suggests otherwise. Even the polarimetric imaging system aboard Japan's Subaru telescope failed to detect rotational scattering, a subtle but expected polarization shift in reflected sunlight as surface angles change. The system saw no shift at all. The object is moving, it's emitting, it's interacting, but it's not rotating, not even slightly. In astrophysical terms, this is a paradox. A body large enough to survive solar proximity, fast enough to escape gravitational binding, and dynamic enough to bend magnetospheric plasma, yet perfectly motionless in its own frame. A comet that does not spin, an interstellar object that does not tumble, a body in a space that behaves more like a sensor than a stone. By November 7th, 2025, the global scientific community had assembled a puzzle, one so carefully laid out, yet so deeply contradictory, that even the most grounded researchers were now privately admitting what they couldn't say aloud. The object known as 3I-ATLAS had defied almost every expectation. It had passed through 3 consecutive coronal mass ejections with no debris. It had altered its trajectory with no visible force. Its brightness drifted without reason. Its rotation was missing. Its oxygen band was filtered. And when it passed Mars, the most watched planet in our solar system, every probe turned silent. Each of these anomalies, standing alone, might be explained. Together, they form a pattern. And at the centre of that pattern lies a question no one in an official capacity is willing to ask. What is this object really? Astronomers have always maintained a high bar for evidence. Science doesn't leap to conclusions. It demands repeatability, peer review, and falsifiability. Labels like artificial or engineered carry a heavy burden, and rightly so. But even within those constraints, the silence has grown louder. Behind closed doors, researchers are now whispering terms once relegated to science fiction. Non-gravitational propulsion, frequency masking, passive shielding, intentional signal modulation. Terms that imply not a rock, but a response, not chance, but choice. And it isn't just the object's behaviour that disturbs, it's the timing. 3I-ATLAS arrived in the same decade that Earth has launched more probes, deployed more sensors, and connected more telescopes than at any point in human history. It threaded its trajectory through Mars orbit, solar CME paths, and Earth-aligned instruments with an elegance that, if accidental, strains coincidence. More critically, it followed two other interstellar objects, 1I Oumuamua in 2017 and 2I Borisov in 2019, both of which had their own minor anomalies. But 3I-ATLAS didn't just echo their mysteries, it escalated them. Each event more measurable, more calculated, more direct. Some are now looking backward, reviewing archived radio telescope logs, revisiting light curves dismissed as noise, cross-referencing government databases long buried under bureaucratic clutter, because maybe, just maybe, the data has been there all along, we just weren't ready to see it. Which brings us to the real question. Not whether the object is artificial, not whether it was built, not even whether it was sent, but something more fundamental, more uncomfortable. The question no one wants to ask. What does it want? Because in physics, nothing happens without cause. An object doesn't blink out of visibility for one exact frame unless it was meant to. An energy signature doesn't echo with Fibonacci harmonics unless it's shaped by intent. An orbital path doesn't correct mid-flight unless it needs to. The deeper fear isn't invasion or surveillance, it's irrelevance. That we are not the audience. That we are simply here, watching, observers of a process unfolding far beyond our consent or comprehension. That whatever 3I-ATLAS is, it may not even see us. Or worse, it already did, and it moved on. On November 8th, 2025, a new trajectory update placed 3I-ATLAS on a course toward the outer heliosphere, its speed recalculated at 59 kilometers per second and rising. But a secondary model, quietly uploaded by an independent researcher, showed a minute change in course, one that, if sustained, would bring the object back into Mars orbit in 11 months. Not a flyby, a return. And so the question lingers, unspoken in headlines, buried in technical papers, passed quietly between those who spend their lives staring at the sky. If this was a message, was it meant for us? And if it wasn't, why did we see it?